Welcome back to chemical bonding. In this section, we're going to do Lewis structures, and some of you may remember doing those in high school. I don't know if you did it the way that we do it. You're welcome to do it however what works for you, but we found that this technique, we call it the NAS method, actually works for everything, even those that are exceptions to the octet rule. So all will be explained. So the Lewis structure shows how the valence electrons are distributed in a molecule and which ones are being shared and which ones are lone pairs and things like that. And it's very useful because it allows us to predict the shapes of the molecules. And if we can predict the shapes, we can also predict some of the properties of those molecules. On bonding, it shows us how we can achieve the octet of valence. Octet means 8, and most all of the elements that are binding together want an octet, unless they just don't have enough electrons. Usually hydrogen only needs 2, but everybody else pretty much needs 8 electrons around them, either sharing or taking themselves in order to feel like that they are stable and they have a full octet. So the Lewis theory allows us to predict which atoms will be most stable when they get their octet of their valence electrons. So the octet rule is really important. When these things bond together, they are going to either be gaining, losing, or sharing electrons. And they try to achieve what we call the noble gas configuration. If you recall, the noble gases are in that last far right column, 8A, and they have a full octet. That is, they have an S2P6 configuration. So since they have a full octet, they're really not interested in giving away electrons or taking any more because they have the octet, which is what all of these elements are trying to achieve. So the nonmetals in the second period, they obey the octet rule, that is 8 valence electrons around each atom. There are exceptions to the octet rule. One is expanded octet, odd electron species, and incomplete octets. So expanded means more than 8. Incomplete is less than 8. And odd electron species are things like superoxides and other things that we don't really talk about in here. So we're going to focus primarily on those that follow the octet rule, or they violate it by having more than 8 or less than 8. So when we're writing Lewis structures for molecular compounds, that's covalent compounds, we write the skeletal structure, and it's important that we're going to put the least electronegative atom in the center, okay? So you look at it and you can see where it is. You don't even have to know what the number is. You can look and see, okay, electronegativity is high and right. I know fluorine is the highest electronegative, so look at it on the periodic table. This is why we did that before, and figure out which one would be the least electronegative, and that's going to be in the center. Exception to that is hydrogen is always going to be terminal, okay, because it can only form one bond. All right, otherwise the more electronegative atoms are going to be terminal and attached to the central atom. So I have these detailed instructions, and then I'm going to have a summary slide on how to do these Lewis structures. So if you need to read a whole lot, you can. But the NAS stands for needed, available, and shared. So the needed ones is the total number of valence electrons that each atom wants to have to be complete. So most are going to be 8. Hydrogen will be 2. Okay? Then you determine the total number of available valence electrons, okay? And so that's the number of valence electrons that they're bringing in, and remember you can find that by looking at the group number. Then you subtract A from N and you get S, and so that number is how many they need to share between them. Then you distribute them among the outer atoms first, and then put them on the central atom, because only the central can violate the octet rule. None of the terminal elements can violate the octet rule. All right? And so, as I said, so if you don't have enough electrons, or if you have too many electrons, they all go on the central atom in pairs. Some can form multiple bonds. Double bonds, those are going to be your pecons: phosphorus, carbon, oxygen, nitrogen, and sulfur. They can form double bonds. So you're going to look at that first before you start doing anything too crazy. Then the triple bonds can be formed by the cons: carbon, oxygen, nitrogen, and sulfur. So double bonds are pecons, triple bonds are just cons. Only the central atom can violate. So if you have any left over, even if it's going to be more than 8 on the central atom, that's where they're going to go. If you follow these rules, you can write the Lewis structure for anything. So here is the sheet that you can kind of look at as you're going with the NAS method. The needed, the available, the shared, and then if you divide the shared by 2, that'll tell you how many bonds you're going to have. Now remember, sometimes you're going to have multiple bonds, and sometimes you're not going to have, that's not going to give you the right number. If the bond number looks odd, that's probably because it's going to be an exception to the octet rule. All right, so let's do some. Okay, so write the Lewis structure for carbon dioxide. So the first thing we're going to do is we're going to write the skeleton. So I know that carbon is the least electronegative, plus carbon's almost always in the center. So it's going to be COO. That's my skeleton. Then I'm going to do the NaSB. How many does it need? I have 1, 2, 3 elements that are not hydrogen. Each one of those is going to need 8. So that's 24. Okay, each one of those needs 8 to feel satisfied. How many are available? Now what I do is I look and see, okay, oxygen is in group 6, so it has 6 valence electrons. Carbon is in group 4, and then another oxygen is in group 6, and that gives me a total of 16 electrons. The shared is going to be N minus S, or 24 minus 16, and that's going to be 8. And so according to this, it's predicting that 8 divided by 2 is 4 bonds. So when I look at my carbon, I see that I have oxygens and I have carbons. I only have 2 bonds written right now. It says I need 4 bonds. I need to ask myself a question. Can it form double bonds? Well, it is PCONS, so it's a carbon and an oxygen, so it can form double bonds. So I can have 4 bonds by doing that. Now, once I've done that, I'm going to put the electrons around the terminal ones. Now, this is a very important step here. we're going to go back to our available because these are all the electrons we have to work with. Okay, so I have 16 to begin with. All right, remember each one of those lines equals 2 electrons. Okay, because that stands for a bond. So what I have drawn right here is 2, 4, 6, 8 electrons in bonds. All right, so that leaves me 8. So I need to finish the octet on the outer or terminal elements. So this oxygen thinks it has 4 because it has 2 bonds. So it needs 4 more electrons, and I do those in pairs. And I look at the other one, and it's the same situation. All right, and so I just added 8 more. And so now I'm out of electrons. And if you notice, carbon thinks it has 8 because it's got a double bond on that side and a double bond on that side. And that is 8 electrons. Okay, and so you can do the Lewis structure for NH3, ammonia. There's a for practice for CO. Sorry, my bad. All right, so I'll do this one for you. So this is NH3. Hydrogens have to go on a terminal end, okay? So that means they're going to be attached to the central atom. So I'm going to write my skeleton. I'm going to do NaSB. So nitrogen would need 8, but the hydrogens only need 2. So I have 3 of those, so 2 times 3, which is 6, and so that's for a total of 14, right? 8 plus 6 is 14. Then available, I look at the group numbers. Each hydrogen is 1, so 1 plus 1 plus 1 plus, and the group number for nitrogen is 5, and so that is 8, and this was 14. Should write that down. And I kind of line them up like this because then what I can do is I can just subtract them. All right, because it's going to be 14 minus 8. And then 6 divided by 2 is 3. Why are we dividing by 2? Because this is the number of bonds, and each bond has 2 electrons. Okay, so then I go back to my available number, 8 minus, I've got 2, 4, 6 electrons in bonds. And so I don't have any more electrons to put on the terminal because they can only do 1 bond. I can't put any more electrons on the hydrogen. I have 2 electrons left, so I'm going to put both of those on the central atom, and then that gives nitrogen its octet. And I've run out of electrons. So those of you who like rule things, you're going to really like this because it works every time, and that doesn't happen too often in life. And then I have another practice for you there. So sometimes we need to write Lewis structures for what we call polyatomic ions, and so when we have something that's ionized, that, remember, that it changes the number of electrons that it has by whatever the charge is. So if you have a positive ion, remember, you have lost electrons. If you have a negative, you have gained electrons, and it's ever how many the charge is. So for polyatomic ions, it's pretty much the same, except there's a little bit of different convention in writing it. So you have NH4. So I'm going to have to put H's all around the hydrogen. And that is my skeleton. And then I've got NaSb, and so that's going to be 8 plus 2, 4, 6, 8 is 16, right? 4 times 2 is where that came from. And then available is 5 plus 4, because there's only one valence in those. Now that gives me 9. And if I subtract that, I'm going to have an odd number. I can't have an odd number. Okay, I've got to have a pair of electrons. So what is it that's different about this that I did not take into consideration? It says it's a plus. If it's a plus 1, that means that I lost an electron, which means I only have 8 electrons. So then 16 minus 8 is 8, and 8 divided by 2 is 4, and I'm showing 4 bonds. And so 8 minus 2, 4, 6, 8 equals 0. So if you have something that is an ion, you have to make sure that you take into account. If you get to this point right here and this S number is odd, then you know you've done something wrong. So you need to go back and look at it and see if there was a charge on it or something like that. Okay? Because this number has to be an even number because it's going to be paired electrons. And there's your practice for CLO. And that's it for Lewis structures.